Welcome to this module of relief sizing. So earlier we have studied about what is relief, what different kind of relief methodology available. We did the classification of relief and we have discussed the various relief scenarios. So in this particular chapter we are going to discuss with the relief sizing. Now basically relief valve, they are designed to allow the flow of fluid from the vessel whenever the vessel reach the preset pressure, that is MAWP. We have discussed already, that is the maximum allowable working pressure. Now this allows the removal of excess energy in particular span of time from the vessel to prevent the further pressure built up. Now usually the valve are designed to close when the pressure inside the vessel reaches the safe limit. So we have already the set pressures, etc. Now the first step in sizing relief valve is to determine the corresponding required mass flow rate that would be sufficient to release the overpressure in a specific interval of time. Now the required orifice area for a relief valve or rupture disc is determined by this particular formula. A is equal to bar m upon kd g naught, where m naught is the required relief mass flow rate and usual units are in terms of mass per time. Kd is the discharge coefficient that accounts for the difference between the predicted and the actual mass flux in the valve and usually provided by the manufacturer. And G naught is the theoretical mass flux having the unit of mass per unit area time. So whenever there is a need to calculate the G naught, it can be calculated by the Bernoulli's equation for the fluid, and that is the G naught is equal to P rho naught square root of minus 2 limit from P1 to Pn integration dP upon rho, where P1 is the pressure at the entrance of the valve and Pn is the pressure at the nozzle exit. So whenever you are using the nozzle, rho and rho n is the fluid density at the pressure P and Pn respectively. So only standard sizes of valve nozzles are available commercially and calculated area would not expected to match those sizes. So practically 10% as a safety factor is applied to the calculated area. Then the closest matching size is selected. So we have discussed previously that the relief area must neither be too large nor too small to omit the chances of excessive flow or chattering in case of large sized nozzle and compromised overprotection in case of a small sized nozzle respectively. So this is the prima facie requirement. Now let us say an oversized valve is selected, then the actual flow rate due to the larger area will be significantly greater the desired rate for which the system is designed. So when the fluid flow through the piping system due to higher flow rate, there will be a greater pressure drop along the entrance and exit point of the piping system. So this excessive pressure drop can pose a serious effect on the stability of the system. So usually those calculations which we have discussed, they are performed by assuming a steady state flow through relief valve, and the flow rate is taken 1/10% of the relief set pressure. Now whenever we are discussing this particular aspect, we should give a due care to nozzle models. So for specific processes, there can be a various relief scenarios that constitute the limiting case. Lots of thermodynamic, physical, chemical and reaction kinetic data are involved while we go for these relief devices. To simplify the analysis part, various assumptions are required which is discussed separately in the given reference, that is Industrial Hazard and Plant Safety by Sanjay Banerjee, and we are going to discuss these things in sequential manner. So first let us take the frozen flow. Now frozen flow is one of the extreme condition for chemically reacting hypersonic flows. Now the reaction rates are so low and the time required to complete the chemical reaction is so large that the composition of the mixture at every point in the medium is completely determined by the mass fluxes, both the convective as well as diffusive mass fluxes. Now, the time required to complete the chemical reaction is larger than the time required for the fluid to pass unit distance with the hypersonic speed. Then we have to consider the equilibrium flow. This type of flow arises in just opposite condition to the frozen flow, and can be said as the other end of extreme condition, where the time required to complete the chemical reaction is too small than the time required for the fluid to pass the unit distance with the hypersonic speed. So, these equilibrium model can be used for such type of flow. There are certain non-equilibrium flow. Now, this type of flow is usually seen in the practice where the time scale and the flow scale are found in the same order. So, the modeling of non-equilibrium flow is difficult as no direct mathematical equation is available as on date for the further calculation. There is a flashing flow when the evaporation of liquid start occurring due to the pressure drop. Sometimes you may have a higher pressure and the fluid moves from higher pressure zone to all of a sudden a low pressure zone. So, this result due to the thermodynamic and mechanical non-equilibrium by virtue of the difference in temperature and velocity of the both phases. The rate of evaporation is affected by amount of nuclei present on the liquid surface and superheating. There is a concept of subcooled liquid. This liquid below its normal boiling point is called subcooled or undercooled liquid. This is a well known thermodynamic phenomena. So, the total heat is accepted by liquid when boiling is consumed to increase the temperature of the liquid. So, subcooled stage is very helpful in refrigeration as it allows the refrigerant to come in same phase for the next cycle. So, the energy efficiency in that particular case can be improvised. Now, saturated liquid for a given pressure when liquid and vapor phases of fluid are in equilibrium with each other, then that the state is called the saturation state. And sometimes it is quite evident in the steam table that you may be encounter this saturated liquid concept. Now, a small addition of energy after the point led to gain the liquid a new stage known as superheated stage of the liquid, and it turns into the vapor at constant temperature. Now, here this particular diagram clearly shows that the different aspects of all thermodynamic stages. Here at the x-axis the pressure and the volume. Sometimes you may have experienced this is the solid and vapor phase, solid phase, and this reflects the temperature effect. So, you may have the critical state, critical temperature. There are several constant pressure lines, etc. So, by slight variation in any of the parameter, pressure, volume and temperature, you may have a change in different type of thing like from subcooled to saturated to superheated, etc. Now, remember these type of diagram, they are extremely useful for performing thermodynamic calculation, because the pressure, volume and temperature, these are only things which you can measure directly, which you can alter directly. Otherwise, rest other things like internal energy, enthalpy, entropy, these are available in terms of correlations. So, you have a liberty to alter all these pressure, volume and temperature in due course of time. So, while we calculate or while we go for any kind of thermodynamic calculation, we need to take several assumptions. So, now let us have a look of those assumptions that fluid below the two phase level, if one exists, is well mixed as is the vapor above it. Now, if level reaches the relief device, then the vessel will be treated as well mixed. Now, the discharge stream is usually somewhat richer in vapor, that implied by the homogenized vessel assumption. So, such vapor disengagement in turn lead to the somewhat, you can say, the smaller relief devices. Discharge line will be treated as if two phase flow, if it occurs in them, is homogeneous and in equilibrium. So, at high discharge rates that occur during the emergency relief, this is reasonable, particularly in the vicinity of the pressure maximum. So, for lines or a nozzle less than 100 nanometer in length, this assumption is not made, but a semi-empirical correction applied. The homogeneous equilibrium assumption allow the analytical solution for discharge rate that is therefore useful. Another assumption is that the relative volatility of the vessel contents does not change during the relief. Now, this assumes boil of one predominant component. Correction will be introduced where necessary to account for gases that may form during the reaction. Now, another assumption is that vapor density is much smaller than the liquid density. This is true only at the relative low pressure and should be reassessed when liquid density rho f is less than or equal to 5 to 10 rho g, that is the gas density. Now, another assumption that vapor liquid equilibria can be calculated using the Clausius-Clapeyron equation and the vapor gas mixture can be treated as ideal. Now, Clausius-Clapeyron equation is one of the most fundamental equation in thermodynamics. Now, these assumptions are not essential, but simplify the formula and are consistent with the level of the order of assumption. Now, thermophysical properties can be assumed approximately constant at their average values between set and maximum pressure condition. This is another assumption. So, various models have been discussed by Ron and Darby, and you can have a look of those models and the reference is given at the end of this particular module. So, few of them are discussed in the next slide. Now, first methodology is the omega method. This method was derived for the single component fluid and assumes that the density of the two phase mixture can be represented by a linearized equation of state. Equation of state, they are much popular in thermodynamics because they represent the correlation of measurable to non-measurable quantity. Now, there are some points need to be remembered. One is that the care should be taken while calculating data as the equation developed are based on the analytical evaluation of the mass flux integral using an approximate linearized two phase equation of state for the fluid density. Another is that accurate thermodynamic and physical data is required, as these data are used only at initial step of calculation, while further calculation are based on the result obtained from the first step, which we have discussed in the previous slide. Now, as this method assumes a single phase calculation, the linearized equation developed may not give accurate two phase density versus pressure data for some condition due to the extrapolation of the data. So, this is again a very important point. Now, the accuracy depends on the nozzle condition and nature of the fluid as well as the pressure range where nozzle is functioning. Now, this method is used for fluid in between low to medium pressure range. Now, this method is not at all feasible in the region near to the critical point. With this particular point we have discussed in the previous diagram. Now, this method is also not useful for dense gases that condense easily in concerned pressure region. So, we have discussed the pressure region in that particular diagram. Now, it is also not appropriate for mixtures with light component gases such as hydrogen, etc. There are slip conditions and non-equilibrium calculations are not accounted in that particular model. So, appropriate correction need to be incorporated while we go for higher calculation. Now, the modified version of this particular method, that is the omega method, API method, is used for the calculation of multi-phase fluid. Now, let us have a discussion about the API. API stands for American Petroleum Institute. So, API method. Now, for flashing liquids having the boiling point at normal atmospheric pressure greater than 340 Kelvin, the omega parameter is determined for two phase density of the fluid at two pressure P0 and P9. Now, where P9 is equal to 0.9 P0 and the constant entropy. So, entropy remains constant throughout. Now, there are some points need to remember while we use this API method. So, number one is that the choke pressure is estimated through omega method, and this could announce some error in the calculation. So, while we go for the precision, then we need to take due consideration for those errors. Now, second point is that the density of two-phase fluid is calculated at 2 points using single thermodynamic property. The third point is that an appropriate property database must be used to determine the density and quality, that is represented by X at two separate pressure at constant entropy. The penultimate point is that accurate thermophysical data is required, since small variation in the thermodynamic properties can have a large effect on the density value. Now, this is again a very crucial. The reason is that sometimes a small variation in any of the thermodynamic property may have a large impact on the density. So, we need to be very careful while using this particular aspect. The last point is that non-equilibrium effects are not included in these particular model. So, we have to give a due consideration for all those points while calculating this particular aspect. Now, next is the two-phase homogeneous model, referred as TPHEM. Now, this two-phase homogeneous model is a computer-based model, and the mass flux is evaluated numerically by inbuilt program using the density of liquid and gas vapor and the mixture quality of at 2 or 3 different points, that is P0, P9 and P2. There are some points which we need to be remember while using this TPHEM method. Number one is that this model can applied for frozen or flashing flows as well as for the subcooled or a saturated liquid. Now, variety of conditions such as nozzle flow for inviscid or viscous fluid can be run in this particular program. The third point is that it includes slip parameter or non-equilibrium parameter. Fourth is that multi-component system can be handled in this particular program. And the last one is that choke point may not be accurately determined because the calculation is based on density pressure fitting equation. So, once we have this particular equation, then we have to give a due consideration of this last point. Another model is the homogeneous non-equilibrium model, that is HNE model. Now, this particular model is based on energy balance of the flashing liquid. We have encountered and we have discussed the flashing concept in the previous slides. Now, the rapid generation from flash is assumed to result in choke flow, and the mass flux is evaluated from the definition of the speed of sound using the Clausius-Clapeyron equation to relate the vapor density to vapor pressure of the flashing fluid and the thermodynamic properties. So, whatever thermodynamic properties are required, we can use this particular model. For slightly subcooled liquid, it has been observed that the actual mass flux may be assumed as 300% greater than the predicted by any of the model which we have discussed previously. So, it is applicable for single phase, subcooled or a two phase mixture. Now, it is applicable for flashing but non-condensing flow conditions. So, be particular about this the use of this particular model. Now, it predicts the effect of non-equilibrium condition. Usually, it minimizes the amount of input data required for the calculation. Usually, calculations are extremely easy to perform. The choked pressure is assumed to be the saturation pressure, but this is not always appropriate, especially for low relief pressure and low subcooling. So, while using this particular model, you must know that what is the concept of low subcooling and low relief pressure. Now, another method is the homogeneous direct integration method. sometimes referred as HDI method. Now this method involves generating the multiple data points P rho x, that is a dryness factor, over an isentropic range of pressure from P naught to Pn. So using a thermodynamic property database for a pure fluid and a flash routine for the multiple component mixture. So these data are used to evaluate the mass flux integral by numerical integration of this particular equation. Now G naught is equal to rho n into minus 2 integration from P naught to Pn dP upon rho to the power 0.5, and this is approximated as rho n minus 2 summation from P naught to Pn into Pi plus 1 minus Pi upon bar rho I to the power 0.5. Now this method can be extended to account for non-equilibrium effects for flashing flow in short nozzles. So for flashing flow we can take L is less than 10 centimeter, that is length. The effect of non-equilibrium is to delay the development of flashing to pressure below the normal equilibrium saturation pressure. So when saturation pressure of flashing liquid is not completely developed, then the quality factor, that is X, is actually lower than that at the equilibrium, that is Xc. So we can represent this aspect by following equation, that is 1 upon rho is equal to x upon rho g plus 1 minus x upon rho L. So if we take that L is less than 10, then x is equal to x naught plus xc minus x naught upon L upon 10, where L is having the nozzle length in centimeter. This model is rigorous within the assumption inherent in the ideal nozzle equation and the HEM assumptions and the precision of the property data, which you can have from various handbooks. Now it is universally applicable for all fluids under any or all conditions which are applicable, for which you are having the property data available. Now the procedure, this particular procedure does not depend on whether the entering fluid is cold liquid, subcooled flashing liquid, or a condensing vapor, or a two phase mixture, or whether or not the flow is choked. So it is simple to understand and apply, obviously, which is evident from the previous calculation. Now it is easily applicable to multi-component system, provided the mixture property data are available for performing the required flash calculation over the pressure range of interest, whatever it is given. Now a process simulator using the property database can be usually generate the required data. The calculation method usually is simple and direct and is ideally suited to the spreadsheet solution. So the method is more accurate than those above because no model approximation for the fluid property is involved. Now let us have a look about the sizing calculations. Now sizing calculation, we use a certain set of equations. We are going through all those equations which are important. Now if maximum allowable pressure is reached inside the vessel, the volumetric rate of vapor generation must be equal to the volumetric outflow through the relief device. That is the rule of thumb. Now the outflow could be a vapor or a mixture of liquid or vapor. Now if Qt is the total heat input per unit time and HLG and rho g are the latent heat of vaporization, Lg stands from liquid to gaseous system, and rho g is the gas density, X is the quality and sometimes it is referred as the dryness factor. Now G is the discharge mass flux and A is the area of the orifice that is attributed to the relief device. Then Qt upon HLG rho g is equal to XGA upon rho g plus 1 minus X into GA upon rho L. Now, if let us take that x is equal to 1, that is all vapor discharged through the nozzle, that is there is no liquefaction, etc. The heat input can be through chemical reaction or external heating. This is again given, or sometimes you may have to take the assumption. Now, if alpha is the volumetric fraction of the vapor in the discharge line, then x is equal to alpha rho g upon rho L into 1 minus alpha plus alpha rho g. So, therefore, if we combine both the equation, we get Qt upon H L g rho g equal to Ga upon alpha rho g plus 1 minus alpha into rho f. So, upon simplification, the A is equal to Qt into alpha rho g plus 1 minus alpha rho L upon G H L g rho g. Now, if we take alpha is equal to 1, that is for all vapor discharge, then Ag is equal to Qt upon G H L g, that is enthalpy from liquid to gaseous phase. Now, for two phase discharge, this equation can be simplified, and if we take a purely one assumption, that is rho L is greater than rho g, then alpha rho g can be summarized to 0. Then this equation comes out to be ALG is equal to Qt into 1 minus alpha rho L upon G HFG and rho g. So, if we take VLG is equal to the volume of the vapor liquid mixture per unit mass, then it can be approximated to 1 upon rho f for this particular case. So, we get ALG is equal to Qt VLG into 1 minus alpha rho L upon GHLG. Now, let us understand the concept of zero overpressure. Now, in this particular aspect, the system can be set at zero overpressure if pressure inside the vessel does not cross the limit needed to the fully open valve. So, at this condition, all the calculation will be performed at the set pressure and the area of relief valve A naught. This can be calculated as, if we take the condition of for all vapor flow, then A naught G is equal to Qt G set HLG. So, we can calculate this one. Now, if we take the condition of two phase discharge, then A naught is equal to Qt VLG into 1 minus alpha naught into rho L upon G set LG, where G set is the discharge mass flux at set pressure, and alpha naught is the volumetric vapor fraction in the discharge at zero overpressure before discharge, and this is called as the freeboard volume fraction. Now, there is overpressure number. Now, it is a dimensionless number which can be defined as the ratio of the energy that can be stored per unit volume of the vessel between set and maximum pressure, assuming no discharge. We may assume that there is no discharge at all. So, it is O star is equal to Cp delta T m naught VLG upon VHLG. So, where this is the overpressure number, V is the volume of the vessel, m naught is the initial mass of the vessel, delta T is the rise in the temperature inside the vessel, and Cp is the heat capacity of the liquid. So, if we take the relatively small pressure and a temperature change, then this equation reduces to delta P upon delta T is equal to 1 upon T HLG upon VLG, where T is the absolute temperature. It is in correlation with the Clausius-Clapeyron equation. Now, let us have a look of about the emptying time. Now, the time required to heat up the vessel to the maximum allowable temperature, that is by delta T, will be delta T H is equal to m naught Cp delta T upon Qt. The time required, this is the time required for emptying the vessel, would be delta TE is equal to m naught upon GA. Now, if we combine both the equations, we get area in terms of temperature maximum, and that is A is equal to QT upon G delta T Cp. So, the ratio between this area and the area at zero pressure gives the value of overpressure number. So, we can redefine the overpressure number, that is O star is equal to A star equal to A naught upon A equal to Cp delta T m naught VLG upon VHLG. Now, let us take the flow area of runaway reaction. Now, if Q is the rate of heat generation for runaway reaction, then A naught is equal to Qm naught VLG upon G VHLG. So, A is equal to Qm naught upon G into HLG into V, VLG m naught to the power 0.5 plus Cp delta T to the power 0.5. The entire thing is under the square. So, A star is equal to A naught upon A is equal to 1 plus Cp delta T m naught VLG upon VHLG to the power 0.5 the whole square, and it is comes out to be 1 plus O star to the power 0.5 square. So, these formula are very useful while relief sizing, and care must be taken in terms of unit consistency and the use of proper data for given condition. Now, little change in the value can drastically change the calculated values and result the failure of the relief fall, and this may be extremely catastrophic. So, first thing must be in mind that we must adhere with the consistency of the unit, and we must use the proper data for selection. Now, in this particular module, we had a discussion about the relief sizing, different type of models we have discussed, and different type of equation we have developed for the proper relief sizing. Now, if you wish to have a further reading, there are references which are enlisted in this particular slide. Thank you very much.